We spend months agonizing over the visible parts of a building, the facade, the height, the interior finishes. But while we admire the architecture above ground, gravity is waging a constant, invisible war against the structure, pulling thousands of tons downward. The earth beneath our feet is rarely perfectly solid. Soil layers consist of varying particles, air pockets, and moisture that compress, shift, and fail when subjected to concentrated heavy weight. This diagram shows the structural load path. The entire weight of the building, from the roof, across the slabs, and through the beams, funnels down and concentrates into the vertical columns. If this highly concentrated column weight is allowed to rest directly on unprepared dirt, the soil will yield under the stress, leading to severe structural instability and cracking as the building settles unevenly. To stop this from happening, engineers design a shallow foundation. Placed just below the surface, this structural system intercepts the plunging weight of the column before it hits the raw earth. This 2D cross-section visualizes safe bearing capacity, the strict mathematical limit of pressure a specific soil type can handle before collapsing. By widening the concrete base, the foundation forces the concentrated column load to disperse into broad, safe pressure waves. Because soil composition and property layouts change drastically from site to site, a single shape doesn't work everywhere. Engineers have to alter the geometry of these foundations to solve specific environmental threats. Let's look at the first problem: a standard structural column resting on stable, reliable soil. The solution is an isolated or pad footing. This diagram shows how it widens the base of a single column into a square footprint, spreading the load into an efficient pyramid of pressure. What if you aren't supporting a solitary column, but a heavy, continuous masonry wall? You use a strip footing. Stretching the foundation geometry into a continuous track beneath the wall ensures weight is dispersed evenly, preventing one section from settling faster than another. Imagine two columns located so close together that their underground pressure zones overlap, dangerously overloading the soil. Instead of separate pads, engineers design a combined footing. Merging both columns onto a single rectangular concrete base safely balances and redistributes the overlapping forces. Building against a property line means the foundation pad cannot extend past the column. To fix this lopsided weight, engineers use a strap footing. A concrete strap beam connects the edge column to an interior column, acting like an underground seesaw balancing the structure. If the soil is extremely weak, or the building so massive that individual footings would punch through the earth, engineers deploy a raft foundation. Replacing individual pads with one giant concrete slab floats the building across the soil, maximizing surface area to reduce pressure. Geometry and load balancing mathematics give engineers the tools to solve nearly any soil condition. But all of this calculated theory is useless until it is physically built. Brilliant structural theory is instantly compromised by flawed construction practices. Execution on site must be exact. It starts with rigorous site investigation and surveying, followed by precise excavation. Crews must dig to the exact depth to reach the approved bearing soil. Next, workers pour a leveling course of plain cement concrete, or PCC. This creates a clean, flat, hard barrier so the structural foundation never touches raw dirt. Then comes the steel reinforcement cage. These heavy rebar grids must be elevated on concrete cover blocks, preventing the steel from touching the edges and rusting from soil moisture. During the pour, workers use needle vibrators to consolidate the mix, forcing out air bubbles that would leave hollow cavities in the finished concrete. Finally, precise water management during the curing phase dictates the ultimate chemical strength of the concrete, securing it before the soil is backfilled around it. Skipping a single quality control check in this sequence creates structural flaws that diminish the load-carrying capacity of the concrete, leaving the building vulnerable to the very forces the engineer worked to counteract. When a foundation fails to spread its load properly, usually due to poor soil checks or incorrect footing sizes, the building experiences differential settlement. This elevation shows the results of that failure. One corner of the building sinks deeper than the rest, triggering a cascade of stress fractures that rip through the walls. Internal execution failures are just as destructive. Poor compaction causes honeycombing, and inadequate concrete cover allows groundwater to reach the steel. The rebar rusts, expands, and destroys the foundation from the inside out. Unlike a leaky roof or a broken window, a failing foundation is an existential threat to the entire structure. Once the earth gives way, it is nearly impossible to repair without extreme cost. A building's true strength, safety, and longevity depend entirely on the unseen engineering buried beneath it. Ensuring that a home survives for decades requires a mandate for qualified structural engineering and rigorous site investigation long before the first brick is laid. Architectural beauty is what we admire on the surface, but uncompromising foundational engineering is what survives the test of time.